Okay, so formally welcome you all in today's session. And in the last lecture, we discussed about the current transformer under the head of instrument transformers. So we discussed that what is the how the instrument transformers are different than that of your conventional transformer, or that in other words is called the power transformers. And though instrumental transformer can be used either for the measurement of voltage or current or the power measurement. When you talk about power measurement, then obviously the combination of the current transformers and the potential transformer both will be used. Otherwise, you can use the potential transformers and the current transformers for the measurement of voltage and current respectively when your measuring system device is directly connected with the high voltage line which is under the measurement in terms of the voltage or current rate. Okay? So when you are connected with the live conductors, particularly across the high voltage line, then it was very important to measure that particular electrical parameter with the highest accuracy, where you cannot afford any mistakes. Okay, what generally, like by extending the range of multipliers or the shunts, you obviously you can use the voltage and current measurement, but that is actually erroneous measurement. So when we particularly interested to measure these parameters for certain applications, we cannot afford those errors that we have discussed. I have told you in the today's slide also we will discuss under the head of potential transformer, as we discussed under the head of current transformer as well. So that is what you remember. Okay, so the objective of today's purpose of discussion is the potential transformer or the voltage transformer. In other words, popular name is potential transformer. So, and what was the number two application of the instrument transformer, which lies over the current transformer and potential transformer as well? That is uh, that is the safety of the human personals. That is the safety of the human personals uh, of who is under the measurement, right? So the primary objective of the potential transformer is the exactly same what the current transformer or the overall instrument transformer is. That is, when we talk about the measurement of voltage across the high voltage line, so obviously you have to bring those high voltages 11 kV, 330 kV, 660 kV or 800 kV in India. You have to step it down before going to apply the measuring instrument. Okay, why we need to step it down? Otherwise, if I'm trying to, even if you'll try, that is impractical. But let's say if I do not bother about the cost, okay, and if you'll say that no, we will straight away go for the measuring that 11 kV or the 330 kV or 44 kV, whatever the line is, then what happened accordingly, you have to invest a lot of money to design that kind of measuring instrument where a lot of high insulation is being used. Okay, because your insulation has to be very very wide. Okay, otherwise you cannot you are going to compromise with the safety of the operational personals. That's true. You may be in danger itself. So that is the primary reason, okay, why you need to step it down to the safe range. And once you have stepped it down, then the secondary panel of the measuring instrument through which you can connect and with the utmost safety, and you can pursue your task. So the when we talk about the potential transformer, these things are not indifferent. It is exactly the same motive and the objectives what we have regarding the current transformers and as well as the overall instrument transformers are concerned. Specifically, when we stick to the potential transformer, the primary winding of the potential transformer is connected across the high voltage line, unlike the primary winding of the current transformer, which is connected through the line, right? And that is why In current transformer, to reduce the number of resistances, number of loops in the primary winding of the current transformer are very less. On the contrary to this, because you are connected here in shunt or in parallel, so obviously the number of windings of the that when I'm talking about primary winding of the potential transformer is very large as compared to the current transformer. Understood? So that you will be match up or with the voltage or as is shown in this particular diagram, the AC line or the VP. Okay, that is the primary voltage. And then what we do, by applying the turn ratio, um, okay, or the transformation ratio, we reduces the number of winding of the secondary side of the potential transformer, so that the potential appear across the secondary side of the winding is very less as compared to the voltage appear in the primary side. So Vs is very less as compared to the Vp. Okay, and so that the measuring instruments can be directly connected, that voltmeter can be directly connected, through which you wanted to measure the voltage in real time. So that is how the combination is being done. Whereas this demonstration is showing that rather than voltage, if you are trying to measure the power, in that case the role of the potential transformer is the pressure coil of the wattmeter. Okay. Like in case of the previous presentation or during our discussion, we have seen that how you can use the current transformer as the current coil of the power measurement, okay, as far as the live conductors are concerned. Clear? So, the following things you have to be take care. Number one, attenuation ratio must be accurately maintained, okay, because it will affect the accuracy of the measurement. Then the voltage drop in the winding must be minimized. What is the reason behind it? So that you can reduce the effect of the phase shift error and the ratio errors, like we discussed in the current measurement as well. Okay, so the voltage drop in the winding can be reduced. How you can reduce it? This by properly designing the with the minimization of the leakage reactance. Okay, why the leakage reactance? You talk about the minimization because amount of the resistances are in. Okay, and then you can also have to take care about the um, copper conductors, right? So the size of the copper conductor, and by minimizing the leakage of reactance, you can reduce the problem of the voltage drop. That can certainly affect over the or contributes over the phase shift error and the ratio error. Number three, loading in any potential transformer or PD is always very small. Why small? Because the secondary side, the number of turns are very less. So you need not do much bother about, like in case of this problem occur in the current transformer. But still we have to take care of the things because of the heating phenomena. Still certain amount of power dissipation is there. And then the number four, the overall rating or the capacity of the potential transformer, how much it should be. So it should be designed in such a way that it should be 2 to 3 times of the their normal rated values. Yeah. So whatever normal rated values it should measure, it should be designed in such a way that it can measure 2 to 3 times of higher value in case of some abrupt condition or abnormal conditions. Yeah. Or during the some spikes occur. Why spikes occur? Or due to the hormones or disturbances. So this is the theoretical, you can say the equivalent circuit, electrical equivalent circuit of a PT, like we have drawn in case of the CT as well. So I hope that these things you can appreciate very easily. We have discussed these things in a very detailed way under the head of ideal and the actual transformer also. So I appreciate that you can have it. If you have any doubt, you can revert back and discuss uh, these doubts during the last session of the module 4. I don't think that you should find any difficulty. All the symbols or nomenclature have the standard nomenclature. So that way, I would advise that you're in time again and again you understand. Anyway, And their symbols have all the standard nomenclature as we have discussed in case of current transformers as well. Okay, so I'm replacing all these things from the discussions. If you find any difficulty, that is the standard phasor diagram of a PT like we have discussed in case of the current transformers. So I'm skipping this part as well, uh, with an assumption that you will be able to have the fundamentals will be the clear. Okay, and what we will focus now, that we will refer this figures 3.16 which represent the phasor diagram of a PT to the modified, or in other words what we call the expanded view of the phasor diagram of a PT. As you can see, it is shown in the figure number 3.17, and from here if I am going to draw the phasor diagram or the magnitude plot of this particular phasor diagram. So you can appreciate that VP bar is nothing but it is VP bar plus IPRP plus IPXP. Now that is the primary side. You know the relationship of the secondary side as well. So substitute the secondary side n times of S E is equal to, similarly the IPRP and IPXP will remain same, and from here we can substitute the value of ES, that is your VS plus IS RS plus IS XS. Okay, all are coming from this part here itself, denoted, and then we will substitute those values, solve this permutation combination. So you can appear the expression number 3.12. You can cross examine these things at later angle. And then we also know that angle of OCD is approximately nothing but it is the beta. Okay? Angle of O, or in other words, this part I am talking. Okay? So angle of OCD is nothing but it is approximately equal to the beta angle. Okay, so see, this is the exact beta, this part, and this part is representing the approximate beta. So remember, it is approximate beta. Okay? And similarly, it is the approximate delta. Now, what is beta and delta? As usual, as we have been told you in the nomenclature, delta is nothing but it is the phase angle between the secondary winding voltage and the secondary winding current. Beta is the phase angle between the primary load current and the secondary terminal voltage, and alpha is the phase angle between the no load current and the flux. Or the standard nomenclatures are symbol of this exactly same representation what we discussed in the current transformer. Substitute those values, take this approximation, then we can get this expression over here. And if you, even if you will further substitute it, I would say that you can achieve the equation number 3.15, where Vp is equal to n times of Vs secondary voltage plus Is upon n of Rp cos delta plus Xp sin delta, plus the terminology in terms of, or the, you can say that the contribution in terms of the core loss component and the magnetizing current is how much we are getting, ICRP plus IMXP. Okay, so if you will substitute these values, then the actual voltage transformation ratio, which is the ratio of Vp by Vs, from equation number 3.15, you can modify it in terms of Vp by Es. So how much you are getting? It is n plus this rest of the component in a modified statement. So that is the actual voltage transformation ratio of a PT, which is under the measurement of the voltage line. Now, for the simplicity, I would advise that you modify the equation 3.14 over here, okay, rearrange in this way. And if you are going to rearrange in this way, then obviously the VP will be also rearranged as compared to 3.15. And accordingly, if I will rewrite that transformation ratio, so that this transformation ratio can also be written as n plus n of is rs delta plus xs sin delta. So obviously remember that the motive of the 3.16 and 3.18 is exactly same. Okay, so you can refer whatever equation as per your requirement or as per your need. Most of the time, you may have to refer the 3.18 to the operational requirement. Clear? So now you know the actual transformation ratio. So can we find out the errors? Yes, the error is nothing but ideally it should be zero, but it should be actually practically it will be equal to the difference of R, which is the voltage transformation ratio, and the turn ratio, that is R minus N, because theoretically both should be same but practically won't. So how much difference? It will be R minus N as it is represented in the equation 9, or in a modified equation which is little simpler to write directly. Clear? Now, tan angle, you already know that from that expanded view of the phasor diagram, that is AB upon OA. So, I will again substitute those values, modified that particular statement, and rearrange that particular statement again. Okay, so, I am skipping these discussions. I would advise you that later on go through it, because each and every statement is given over here. Carefully solve it, and still, if you have any doubt, you can bring back to me. So obviously, if the theta is tending to 0, very small, okay, this is not 0, so obviously it is a theta denoted. So we can assume that tan angle or tan 0 theta will be tending to 0. So sine by cos, so obviously it is tending to 0. So in that case, I can modify the tan angle theta, so into the approximate value of theta, and therefore the phase angle can be directly represented as in terms of the secondary parameters. Remember, why secondary parameters? Because human personnel is involved in the secondary side of the winding. So whatever the parameter you will get, that is the in terms of the all the secondary values. If you look at this standard nomenclature diagram, so you remember that you are in this side. Okay, this side is connected with the high voltage line. So if I am getting these parameters, can I get do the measurement? Yes, you can do the measurement. But point is that is there any purpose to getting these values directly? No, because then you are going to compromise with the safety of the human personals. Okay, and then again those things you have to use the large size of conductors. You have to compromise with the safety. Then it is no purpose of designing the PT and CT. So whenever you are using CT PT, so remember that you most of the expression we are trying to get in terms of the secondary parameters, so that we can calculate here directly with across the live conductor. I hope that this thing is clear to you. Okay? That is the reason that why you see that most of these parameters we try to substitute or remodify our equation in such a way that this phase angle error can be represented as or the tan angle will be can be represented as, or the transformation ratio can be represented in terms of the secondary values. Okay, yes, IC and IM, that is the exception, because these are representing ultimately the losses. Yeah. So what are the possible errors? The same thing, that the ratio error and the phase angle error. Okay, how can you minimize it? So obviously these errors occur in the due to the primary circuit of the winding, and cannot be obtained accurately. Okay, by simply applying the multiplier device across the voltmeter, and that is why by maintaining the turn ratio of the potential transformers, you can measure these errors very accurately as far as the ratio error or the phase angle errors are concerned. Clear? Reduction of the errors. Yes, we can reduce these errors. Obviously, these steps you have to be taken care. Okay, one, that we should try to we should design our potential transformer in such a way, particularly the secondary side of the connection, in such a way that the losses because of the component part, that is due to the core loss, I would say, or and the losses because of the magnetizing impact. So the losses due to the IC and IM, the parameters you are measuring, those magnitudes should be as less as possible. Okay? That means what? That is the no load component of the primary current can be achieved by the reducing the length of the magnetic path of the core. So this length should be as less as possible. So if you are going to increase the distance between the measurement of the primary and secondary, so remember it will add more errors. Okay, more magnetizing current. Okay, so and also along with that, the length should be less. The connecting wire length should be as less as possible as it is required. And then number two, good quality of the core magnetizing material you should use. Yeah, so that you can reduce these errors. Winding resistances, you also have to taken care. So number of turns, winding leakage flux, you also have to taken care of this, because it is directly related with the insulation requirement. And then the sufficient amount of high flux density in the core, you also have to be used. Clear? Over the winding one cores, because this will help you to reduce the winding resistance impact. These are the things you have to be taken care as in case of the current transformers as well. Is both the measurements are same? No. In case of the current transformers, you know that the number of turns in the primary side is very less and it is connected in series, and that is why it was advisable that you should never keep secondary side of the current transformer even during the unused condition open. It should be always be short circuited. Yeah, for the especially for the safety of the human personals. That is not there in case of the potential transformers is concerned. Remember, okay, because the secondary side is very number of turns is very less. So even if you are keeping it open, there is no problem at all. That is one additional advantage in terms of the human safety. You can say if you at all ignore from the secondary side. But if you are dealing with the current transformer and if you are trying to ignore it, so you have to maybe sometimes compromise with the life of the human personals involved in the secondary sides. Very dangerous. So for our information, if you are trying to summarize the discussions over yesterday, I mean the last lecture and this lecture, this discussion. So there are the almost we can summarize from the six different point of view. The first, the main power line current in case of a city we measured of the nominal range. So the current is stepped down from the primary to secondary. In case of potential transformer voltage, it's obviously stepped down from primary to secondary, right? Primary winding of the current transformer is connected in series, whereas primary winding of the potential transformer is connected across shunt. Clear? To the main line of the sense voltage. Primary winding has the lesser number of turns in the obviously in case of the current transformer. Why? Because it is connected in series. And the primary winding, because you are measuring the voltage, so voltage you can measure across only. So the primary winding has more number of turns as compared to the secondary winding as far as the potential transformer is concerned. That's a matter of common sense. Then the current transformer CT in the secondary side should never keep open, as I've been told you, while it is energized to restrict the accidents over voltage. Okay. The primary potential transformer secondary can be safely opened. Okay. That doesn't mean that you deliberately keep it open. Can be even if it is opened, so it will not too much bother about the uh, life risk of a human personals involved under the operation. Yeah. So while the PT is energized. In many cases, such as bar type, in a single primary winding type or in the clamp type of CT, the primary winding is nothing but it is the main power line of the conductor itself. That itself works as a the primary winding. Okay. So, whereas in all case of potential transformer, a separate primary winding and the secondary windings are necessary. Remember, okay, because connecting current transformer, what happened? You are connected in series, so obviously a clamp you can just hang on with the main power line. It can be itself treated as a primary winding because ultimately it is connected in series. Okay, the primary coil of the CT is connected in series in any way. That's why that is the purpose. Whereas you have to be a dedicated primary and secondary windings as far as the potential transformers are concerned. Yeah. While you are using CT for the measurement of power, so that means when you are using CT as a current coil, the secondary windings is connected in series with the current coil of the watt. Okay. Whereas while you are using PT for the measurement of power as a potential coil, the secondary winding is connected in parallel, obviously, with the pressure coil of the watt. Yeah. So, if you have any doubt, you can discuss with me. Otherwise, I will wind up this discussion here itself, and I would advise that go through with the certain problems given in the book. These all are the formula based problem as far as the phase angle error or that is ratio errors are concerned. Okay, so some formula based expressions you can get. As far as just one information is concerned, as I have been discussed with you the all effect transducers as an additional information from your gate or competitive examination portal. So this is for your information that if you talk about past 5 years or 8 years, most of the instrument transformers has been replaced with the Hall effect transducers because it's a very safe and very less amount of the power management you are required to do. Even the live conductor is there, and there is no question of the safety aspect of the uh, human personals involved in the during the operations. So these things it's obsolete, but is it completely obsolete? No, instrument transformer are still used when you talk about the transmission substations. Clear? Particularly in transmission substations, you can very easily see that these things are being used. I am talking about the latest design, not the conventional design which is there from past 20 years ago. So with this, I'm going to close the today's discussions here itself. And other than this, if you have any doubt, you can discuss with me. And otherwise, I will wind up the